We can bring this whole topic on inflection points, concavities, extrema to a good closure with this function right here. When you look at this function, you know clearly it's an even function. Even function creates a very good sense with regards to everything being symmetric around the y-axis. You have the right and the left side of the graph. It's symmetric around that y-axis, so you end up seeing duplication of values and extrema on either side. But we will not take any shortcuts with this function, x to the 4 minus x squared, and we'll just go everything from top down and take it through to completion. But note, there's no interval provided, so we're not worrying about global extreme values. Everything else will be examined, however. When you look at that function, you can easily start with determination of the x-intercepts. You can isolate an x square, and then you know you'll have x squared minus 1. All of this equal to 0. You have x is equal to 0 plus and minus 1. Those are your x-axis values of your roots. When you plug them into your original function, you'll have 0, comma 0, you'll have plus and minus 1, comma 0. These are your roots of that function. Our good next step should be to determine the first order derivative. X to the 4 minus x squared yields 4x cubed minus 2x. Then the second order derivative can be done and you'll get 12x squared minus 2. You take that first order derivative and you equal it to 0. When you equal it to 0, you'll get an isolation here of 2x. You'll have a 2x squared minus 1. All of that equaling a 0. X is equal to 0. X is equal to plus and minus 1 over root 2. So you have 3 critical point x-axis values, which will give you 3 critical point coordinates when you plug them into your original function. You'll have 0, comma 0. And then you know very well if you put that positive and minus 1 over root 2, because it's an even function, you know you can do the even function test and it'll be an even function. You'll have the same y value duplicated across the positive and the minus x-axis values. And let's determine what that is. It's not going to be hard because you have even powers over there. You put 1 over root 2 over there, you're looking at 1 over 4 minus 1 over 2. You're going to have here a minus 1 over 4 and a minus 1 over 4. You can bring your calculator and you can very well verify that. Anyhow, now we have to classify these in terms of what type of extremes they are. We know they're local or relative, but we don't know which one is maximum, which one is minimum. We need to do all of these three. You can put everything right here with regards to the x-axis value. When you put the 0 in here, you have a negative output. So this tells you this right here is a relative maximum because it's negative. When you put this x-axis value right over here and this one, the square will take care of the positive and the minus and convert everything into positive. You'll have a positive here and a positive here with regards to the output, and you're looking here at a relative minimum and a relative minimum. If you were to look at the graph of it, which would be a good reasonable next step, I have good points here. I have a 0, 0, plus and minus 1, 0, and then I have these extremes. I have a minus 1 over root 2, minus 1 over 4. We can estimate everything here. If this right here is a minus 1, this minus 1 over root 2 is like a minus 0.707. So you're looking somewhere right over here. And then you're looking somewhere right here. These are my three extreme values. This one, and this one. And you have a curve which is going to come like this. Like that. I have my relative max or my local max, which is this. Then I have these two, which are my local minimum. If you did the first order derivative test and you looked at the direction of the tangent lines in terms of their slopes, you have a minus because here the tangent lines are pointing downwards. Then they zero out over here, then they become positive here, they zero out right here on top of this extreme, then they become minus here, then they zero out at this extreme, then they become positive. When you're going from right here minus to a positive, you know you have a local extreme, which is verified by this, which is a local minimum. When you're going from here positive to a minus, you have a local maximum, which you are verifying right here. And then from here minus to a positive, using the first order derivative test, you're looking at a local minimum and it's verifying that. So we have everything verified over here with regards to the local extremes, the local minimum, local maximum, all of that looks good. Now what we have to do is determine the concavities and the inflection points. I'm seeing here between this local minimum and this local max, between this point right over here, there'll be some sort of inflection point, and between this local maximum and this local minimum, there'll be another inflection point somewhere here, and there'll be an inflection point somewhere here, and we have to determine that. The best way to determine that is take this and equal it to 0, because you're looking at that area where the second order derivative changes sign. It changes sign only because it's either going from a minus to a 0 to a positive. or it's going from a positive to a 0 to a minus, and I showed you what the signs were, but you're looking here everything with regards to the second order derivative. Wherever the sign change occurs and you see the 0 is exactly the point where the flip occurred with regards to the sign. So just take your second order derivative, equal it to 0. You have a 12x squared minus 2 is equal to 0. And that specific point will also be where your concavity up and your concavity down will change. Concavity up to concavity down and concavity down to concavity up. Anyhow, you have 12x squared minus 2 equals 0. You have x squared is equal to 2 over 12, which is 1 over 6, and x is equal to plus and minus 1 over root 6. You'll have two inflection points, and we know what they will be: minus 1 over root 6, and then you'll have a positive 1 over root 6, and everything will come right over here. Because it's even exponents, it's not hard. You'll have a 1 over 36 minus 1 over 6, and you'll end up having here minus 5 over 36. And here you'll have a minus 5 over 36. Remember, even function, everything is symmetrical and everything is being duplicated across. Those are my inflection points. Two inflection points. And here they are represented for you: minus 1 over root 6, comma, minus 5 over 36, and 1 over root 6, comma, minus 5 over 36. And these points will very well be right over here. Here's one inflection point, here's another inflection point. Now let's erase this and talk about the concavity intervals. You know, if you were to draw tangent lines over here, the function will be above the tangent line, and that would also tell you you're looking at concave up. But remember also this: the second order derivative with regards to the sign greater than 0, and then this one right here being less than 0. If this is right here is greater than 0, you know you're looking here at a relative minimum, and then you'll have a concavity up. When right here you're looking at this, you know you're looking at a relative maximum, and then you know you'll have a concavity down. Here I'll have a concavity up pointing up. In this part right here I'll have a concavity down pointing down, and then here I have a concavity pointing upwards. But let's determine exactly what we have with regards to the intervals, and it's not hard. I have two concavity ups and I have one concavity down. My concavity up intervals are right here, from minus infinity coming up to this minus 1 over root 6. And then I jump across to this other inflection point, 1 over root 6 comma infinity, but in between these two right here I have a concavity down, which is from right here to here, my concavity down. It will be minus 1 over root 6 comma 1 over root 6. Right over here to right here is my concavity up. From here to here is my concavity down, and then I go back to concavity up. So everything has been solved for you. We have the roots, we have the critical points, 3 of them right here. One of the critical points was actually your local maximum. We have everything here with regards to your local extremes. We have everything here with regards to your two inflection points, and everything here related to your concavity intervals, and everything has been completed for you. Thank you. Have a great day. Bye.